Hi guys, hope all of us are doing great. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. In our discussion today, I'm going to look at some of the characteristics of transition elements. And this basically is going to be complementing on the previous two videos we have done on the introduction to transition elements and some of the properties and characteristics of some of the or a range of these transition elements. Now, in this particular discussion, we're going to look at the oxidation of these specific transition elements down the groups and across the series. And of course, we're also going to look at some of the representations for the reduction potential, particularly perhaps in the first series of these particular members of the transition element. Now, I talked about the concept of oxidation states and oxidation numbers from our previous discussion. Now we're going to look at this one, of course, from a general perspective, whereby this specific oxidation state, for high oxidation states, these are going to become more stable due to the decrease in ionization energy. And as we had decided, of course, from the previous discussion, we are going to look at the first, the second, and the third, of course, a series of these specific elements. And in particular, we're going to see that there's going to be a particular trend of these specific elements in terms of oxidation states and the potential reduction potential. And they listed these specific, of course, elements in terms of a series and groups. And in this particular case, they said that for the first series that we're going to look at, particularly this is going to be ranging from scandium, which is the first member of group 3, basically to that specific member of zinc, which is going to form a last part of the number of groups which we're going to look at. Now, in this particular case, I'd say that this specific trend is going to create a series. So we're going to have the first series of these members being given as that. But from scandium through yttrium, we're going to look at the specific groups, or I'm going to refer to that one as the scandium group. So we're going to have a various range of groups going down that way. So that's going to be running from scandium. Of course, we're going to have titanium, vanadium, chromium, of course, manganese, iron, cobalt, nickel, copper, zinc in that specific order towards the left. And in this particular case, then therefore, we're going to look at the oxidation down the groups. Now, down the group of these specific elements, generally, we're going to have high oxidation states becoming more stable due to increased ionization energy, or due to decrease in ionization energy. And we had said that this particular energy is going to be reducing due to the increase in the number of energy levels. And this is going to create some shielding effect, and therefore the attraction from the nucleus, which is consisting of protons which are positively charged, is going to be decreasing due to the shielding effect of additional energy levels. And in that particular case, it's going to have a consequence of decrease in ionization energy. And therefore, we're going to see that down the group, due to increase in the number of energy levels, this is going to lead to, of course, a decrease in ionization energy. And in this particular case, for a higher state, higher oxidation state of this specific or transition elements that are going to have high oxidation states are going to be more stable. And therefore, we are going to witness this specific trend across or down the specific group. So generally, we're going to expect it, and therefore that the second row and the third row of these specific elements, which are exhibiting higher coordination numbers. So perhaps we can just have that one in this specific sense. So we're going to have the first row, the second row, and the third row, which are going to be appearing generally for various groups. And for the second and the third ones, they are going to be exhibiting what we refer to as a higher coordination number. And in the study of complex compounds, I talked about the concept of a higher coordination number. Or for the formation of complex compounds, we're going to have a higher coordination number. So down the group, they are going to have a higher coordination number. And in this particular case, in addition to that, we are also going to see that they are going to have a higher oxidation states. And therefore, they are consequently going to be more stable than the first row elements which we have listed above. So this is going to be more stable than the first row elements which we have listed above for this one, which is basically going to be the scandium series. Now in this particular case, we're also going to see that if we move across the series, we're going to have a range of these specific members of the M2 positive, which is basically the one with the oxidation state of positive 2. So this particular series are going to be having what we call forming the range of earlier transition elements, and they're going to form a strong reducing agent. So if I may give this one in terms of an illustration, these are the members which are going to be appearing at the extreme left of the periodic table. So these are going to be having what we call the strong reducing agent capability, especially for members which are going to be having this oxidation state. So we're going to have a strong reducing agent. And as we move across the group, we're going to see that for the late transition elements, they're going to become more stable. Therefore, we are going to expect that the stability of this specific of course, states are going to be increasing as we go from left to right. Now, for this particular, of course, elements, they're going to, or particular states, they're going to become more stable across the series, and they're going to form the stable oxidizing agent, which basically we can as well give us a strong oxidizing agents in this particular case. So these are some of the trends which we are going to witness for the oxidation, various oxidation states of these particular elements. And we are going to see that there's a general trend for the oxidation state down the group from the first series to the third one. And of course, that one can be explained from this specific elaboration which I've just given on the board. We're also going to look at the concept of reduction potential. And of course, there are listed a number of characteristics which we are going to look at, especially on the periodic trends. And this is going to give us one of the, of course, particular trends we are going to witness for these various series and groups of transition elements. So I'm going to give this one using the first series, and it's going to assist us try to pinpoint some of the characteristics we are going to witness across the series for various range of the first, the second, and the third series in that particular case. So I've used the member of vanadium and the chromium, and we shall have manganese, iron, cobalt, and copper, given in that specific order. So I'll give the various, of course, reduction potentials. This one is negative 1.19, and then we shall have negative 0.91, and then negative 1.81. Then we shall have 0.44, and then we shall have negative 0.28, and then lastly we're going to have positive 0.34. So in this particular case, we can see that there's a specific an abnormality or anomality of this specific reduction potential across the series. Specifically, we're going to see that it's going to be reducing in the negative value, but particularly for manganese, it's going to have an abnormality whereby we're going to see that it's going to have a relatively larger negative value for this specific reduction potential. And this, of course, this is going to be an irregularity which we can explain in this specific form as the reason for this one is going to be given in terms of, perhaps I can give this one in terms of the configurations. And this is going to be the difference in the filling of the D subshells, which we are going to see later, that is going to create a difference. So we're going to do a comparison between manganese and iron, and of course that's going to be more elaborate for us. So we're going to have manganese having these specific shells of the D, the S2 and D9.